Hello again, my dear students, and welcome back to part number 3 with our p-n junction diode lecture for the electronics 1 module. Now, if you remember in part number 2, we have studied together the concept of ideal diodes, where we have approximated the IV curve of an p-n junction electrical diode into an on-off states. In the on state, whenever the voltage is forward, the diode can be replaced by a short circuit. While in the off state, whenever the voltage is reversed, the diode can be replaced by an open circuit. Accordingly, we have solved together a series of DC and AC circuits while treating our diodes as an ideal diode. However, as you can see here, this is somehow a very simplified model, as we are neglecting all these IV characteristic features and we approximated only in this on-off state. That's why we can consider the ideal diode is the most simple model for an electrical diode. And in order to get more and more accurate results while dealing with your electrical diode, you have to consider a little bit more complex model. What we are going to do in this lecture is we are going to consider 3 different models for an electrical diode. This will be the challenge of part number 3 in this lecture. So let's start with the exact solution. This is, or let me go to this. Okay, this is the typical characteristics for an electrical diode. We have a very, very, very low voltage whenever the voltage is smaller than V naught, nearly 0 voltage. Then the voltage starts to increase once we jump or we move larger than the V naught, which what we call the forward bias. While in the reverse bias, we have a very low current due to minority carrier up to the breakdown voltage, then we have this breakdown. This is the ideal characteristics. Now, how we can use these ideal characteristics in order to solve our circuits? Let's see. Okay, perfect. So, for example, we have a circuit like this. We have a DC source, which is called VDD, and we have a resistance, and we have a diode. And we need to solve this circuit using the typical IV curve, not an approximated one. If we use an ideal diode here, it will be very easy because now, as you can see, that your diode is forward. So what you are going to do is just to replace this diode with a short circuit, and that's all. And the current flowing here is VDD over R, and that's all. But let's try to make an exact solution for this circuit using the IV curve. So now I'm going to turn to my whiteboard and start solving this circuit using the exact model for a diode. Okay, welcome back to this simple whiteboard, and let's start solving this circuit. Okay, what we have, my dear students, is we have a circuit like this. Of course, as usual, please accept my apologies for my too bad handwriting and plotting or sketching. So this is VDD, this is R, and this is a voltage applied to the diode. As usual, I will call it VD. So by making a very simple KVL analysis, you can say that VDD equals to I times R plus VD. Okay, or what you can say also is I, which by the way I can call it ID because this is the current flowing in the resistance as well as the current flowing in the diode, equals to 1 over R times I'm sorry, no, equals VDD over R minus VD over R. This is simply when I get this VD with a minus sign and then divide by R. So VDD over R minus VD over R. If I would like to plot this equation, this equation is an ID, which is the current flowing in the die, versus the VD, which is the voltage drop on the diode. As you can see, this is a linear equation. So if I consider this VD and this ID, this is a linear equation with a negative slope. Of course, whenever you have a linear equation, you just need 2 points to plot. So what you can make is first to put VD equals 0, which should reflect to a point on the y-axis. So the output will be VDD over R. So this is the point, VDD over R. And then let's put ID equals 0, which is a point on the x-axis. So the output will be VDD equal VDD, which is a point here. So your straight line is something like that. Of course, this makes sense because now the relation is a negative relation. So you have a negative slope equals to 1 over R. So this what we call, my dear students, the load line. Okay, but where is the solution? If I have a value for R and I have a value for a VDD, how I can get the current? For example, if this is a circuit in your exam, I told you, please calculate the current. So simply, the current will be in the operating point. Where is the operating point? Let's see. Okay, so now back to the presentation. So the operating point will be the intersection point between the load line and the IV curve. Because if you take care, the load line is voltage on the diode versus the current flowing in the diode. And the IV curve represents the voltage of the diode versus the current flowing in the diode. So both graphs have the same x and y axis. That's why the intersection point, or what we call the operating point, is at the intersection point between the load line curve and the diode characteristic curve. And by getting this point, you can typically know the value of VD and ID, where the voltage drop on the diode and the value of the current flowing in the circuit. This is what we can call that typical solution, the exact solution, or we can call it also the graphical solution. The main issue with this solution is that it needs a very high computational resources in order to implement the solution. You have to plot this curve to scale, which is an exponential curve. Usually this is very difficult to be plotted by handwriting. It's an exponential equation. And then you have to get this intersection point and get the exact ID and VD. That's why this solution, rather than it's a typical exact solution, however, it's very rarely to be used using our handwritten solutions. So what we are going now to do is that we are going to simplify this model a bit. So what we have seen up till now, actually, my dear students, are two extreme cases. The exact model, which uses the typical exponential curve for a diode, and the very, very simple ideal diode model, where you have only an open circuit and short circuit, that's all. However, we can investigate many models in between. These are the extremes models, the most simple and the most exact, but we have many models in between. So let's examine together some of these models. Okay, for example, this is one of the models we have, what we call the piecewise linear model. As you can see, this is an approximated model. Why this is an approximated model? First, actually, we have to take care that we are now focusing on the forward region only. That's why we are plotting here the first quad only. So the first approximation is that we assume that below the built-in potential, the voltage is totally zero. No, the current is totally zero. No current is flowing below the built-in potential. This is the first approximation. The second approximation is that we assume that after the built-in potential, the current should be exponential, but we assume that this current is linear with a slope 1 over RD. As if you remember from part number 2, I have told you that the slope of this curve is 1 over the resistance. So this is 1 over RD, where RD is the resistance of the model of the die. So here we have a built-in potential, which is VD node, or you can call it V node, and we have a linear model. That's why we call it the piecewise linear model, because we assume that this is a linear model after V node with a resistance 1 over RD. And in order to transfer this model into a circuit model, it will look like this. This is an ideal diode. So whenever the voltage is greater than 0, I mean the voltage on the anode is greater than the voltage in the cathode, this will be short circuit. And if it's great, and if it's lower than 0, then this is an open circuit and you don't have current. Then you have this VD node battery, and as you can see, this is in the reverse bias because this is a built-in potential. You have a positive, negative, and you have this RD resistance. So this will model the diode performance whenever the voltage drop on the diode is greater than the built-in potential. If the voltage drop on the diode is smaller than the built-in potential, then typically the current is equal to 0. And if you put in these two terminal V forward equal VD node, then you will find that VD node minus VD node, then the current again is equal to 0. So you have to put between this terminal voltage greater than VD node, greater than the built-in potential, so that you can have a current here. Otherwise, you will not have a current. So this will consider the piecewise linear model. Another more simple model is again to assume this V node exists, but what is after V node is just an short circuit. So you don't have resistance. So the main difference between this model and this model is the resistance. Here you have what's called the forward resistance or the diode resistance RD, but here you don't have this forward resistance. So it will be a model like that, just a diode and then a reverse biased built-in potential, and that's all. So these are the two models, in addition to the ideal model, of course, where you can model your diode. Okay, so in order to examine the difference between these models, let's come to this example. Okay, in this example, I told you that I have this circuit. This circuit consists of a voltage source with 5 volt, a resistance of 1 kilo ohm. What I'm seeking for is to determine the current ID and the voltage drop on the diode, which is VD. But I told you, please solve this example 3 times. First time using a piecewise linear model. And the second time using a constant voltage drop model, which is the second one. And the third time using an ideal model. And I told you that the exact values, if you do this experiment in lab and measure the voltage and the current, the voltage will be 4.237 milliampere, and this is the current, and the voltage will be 0.762 voltage. So what we are going to do now, my dear students, is that we are going to solve this circuit 3 times. In each time, we will consider a different model for the diode. But let me answer the question from bottom to top. So I will start with the simplest one, which is the ideal. Then I will go to the constant voltage, and then I will terminate with the piecewise linear model. Okay. Now let me turn to my presentation slides, to my whiteboard, and start together solving this problem. Okay, that's perfect. Our circuit is as follows. We have a resistance, a diode, and we have a DC supply. This voltage is 5 volts. This resistance is 1 kilo ohm. This is the VD, and this is the ID, the current we are searching for. In the first stage, we are going to solve assuming that we have an ideal diode. So what we are going to do is as following. We are going first to check the state of this diode. Is this diode a forward or reverse? By considering the polarity of the DC source, so the current is flowing in this direction. That means that the anode voltage is greater than the cathode, so this diode is on forward bias. Accordingly, if we are using an ideal model, what you are going to do is that you are going to replace this diode by a short circuit. Okay, so this is a resistance. And this is your source. This is 5 volts and this is 1 kilo ohm. So it's a very, very simple circuit. You have 5 volt, 1 kilo ohm, and then you have this circuit, then the the current flowing equals to the 5 over the 1 kilo. So you have 5 milliampere. And the voltage drop over the diode, it's a short circuit. So VD equals to 0 voltage. So this is the first solution. We will keep this slide because we will return back to it later on. Okay. Now let's go to the second slide. Okay. Where we have the same circuit. This is the 1 kilo ohm. This is the 5 volts. And we have here a diode, as you can see. Okay, that's perfect. Then it's now a constant voltage model. In the constant voltage model, my dear student, what you are going to do is that you are going to replace this diode by a built-in potential battery in the reverse direction and a short circuit. That's all. There is no resistance, if you remember. So here is a battery, and here we have the resistance, which is 1 kilo ohm, and here we have the 5 voltage, and that's all. And based on the question, he mentioned that this voltage will be equals to 0.7 voltage. Again, using KVL, then 5 equals to 1k ohm times I, which is only unknown, plus 0.7. So I will be equals to 5 minus 4.7, which is 4.3 over 1k. So you have 4.3 milliampere. And the voltage drop on the diode here is typically the 0.7, so VD equal 0.7. Perfect. So let's do the next stage. Okay, so again, let's plot the same circuit, which is resistance, a diode, a voltage source. So this is 5 volt, this is 1k, and this is our unknown. Here we are assuming a piecewise linear model. In the piecewise linear model, what you are going to do is that you are going to replace this diode with a built-in potential. Herein it's given 0.65 and a resistance, and it's given 20 ohm. Then you have your R1K. So now we can replace this diode with a building potential battery and resistance, and then we can complete the circuit. I'm sorry, like this. So I'm sorry, let me make it in a new graph. So we have, this is the resistance, and now we replace it by a diode, and we also replace it with a resistance. This is 20 ohm. This is 0.65. This is the 1K, and this is the 5 voltage. Again, you can use the KVL to answer this question. So you will have this loop. Then 5 equals 1K I plus 0.65 plus 20 I. This is a one known equation. Using a calculator, you can solve it. So it's I equals to 5 minus 0.65 over 1K plus 20. Or it's 5 minus 0.65. I think this is 4.35, I think so, over 1020. The output here, the voltage here is, okay, so using my calculator, we can get this output, which is 4.264 milliampere. And the voltage drop on the diode here is this 0.65 voltage plus I times 20. So we have this 4 milliampere or 4.26 milliamperes times 20. It will give 0.08. Then we have 0.08 plus 0.65. Then we get 0.732. So this VD is 0.732. Okay, so let's now sum up what we have did in this experiment. We have solved the problem using 3 methods. First, we use the ideal diode. For the ideal diode, we have calculated ID and VD, or the voltage and the current through that diode. So if we return to this slide, we found that the VD will be 0 and ID is 5 milliampere. Then we use the constant voltage method. Let me change the band. In the constant voltage method, this one, we get an I equals to 4.3 milliampere and voltage equal to 0.7. Then we use the linear model, the precise linear model. So we get an I equals to 4.264 milliampere and voltage equal to 0.732. Then 4.264 milliampere and 0.732. If we return back to the head of the question, it gives us the exact values for the I and V. So the exact value are 0.237 milliampere and 0.762 voltage. So, as a result, we have this exact value. So by comparing now, you can see that whenever you have more and more, let me say, complex model, you get more and more values near to the exact values. As you can see, the minimum error occurs when you have the linear model, then the constant voltage, then the ideal one. So the main advantage of using these models is to get more and more results close to the exact values. However, if you accept a higher range of error, you can directly go to the simplest one, which is the ideal model. These are the most famous three models used for modeling a diode, in addition to the exact model, which is a graphical model we show in the beginning of this part. Now, my dear students, this is the termination for part number 3 for this electronics 1 lecture in lecture 2, named by electronic diode. In part number 4, we are going to demonstrate various applications for an electronic diode in AC circuits, as well as we are going to illustrate what's called the Zener diode. This will be the final part, part number 4. Thank you very much, and see you in part number 4.